Welcome back, dear friends. Today we are going to talk about another exciting topic, that is the design of distillation column internals. So obviously in this tutorial you are going to learn how to design the distillation column internals, and for the successful design we must have to understand the two phenomena. One is the flooding and the other one is the weeping concepts. So let's first discuss flooding and weeping. So flooding is a condition that occurs in distillation columns at high vapor velocity. So the excessive liquid starts to build up in the columns, which leads the flooding conditions. So almost no liquid flows through the tray, so it drastically reduce the separation efficiency of each plate. So in this condition, liquid cannot get down the column due to the high vapor velocity. So this condition, or this vapor velocity, is set as a upper limit of a vapor velocity of a column for steady state distillation column operation. So this is one condition that is called flooding. And in flooding it also happens that at high vapor velocity the vapor starts to take the liquid itself, and it's called entrainment. Okay. And the second concept is called weeping. It's almost the opposite of the flooding. So in weeping phenomena, the vapor flow rates is low, so as a result liquid starts to leak from the holes of each plate, and it's again reduce the separation efficiency of each plate or each stage. So at extreme conditions, when vapor flow rates are very low, downcomers remain empty and all the liquid pass through the holes, and this is called dumping condition. So to design an optimum or economical distillation column, we have to design the column in a way that we should not encounter all these conditions like entrainment, flooding, weeping, and dumping. Okay, so let's practice with one problem statement. Today I am going to solve a problem related to the distillation of benzene and toluene mixture, that is 50-50 mole percent, and the total flow rate is 100 kmol per hour at a pressure of 10 bar, and the feed is saturated liquid going through the distillation column that has 36 trays, and the feed optimum tray number is 18 from top, and the reflux ratio is 3.88. Reboiler pressure and condenser pressures are given, and the product purity that we require: at top we require 99% benzene, and at bottom 99% toluene. So for this problem, first we will solve it for material and energy balance, and then we will perform column internal analysis, and will specify the design of internal stages. Okay, so let's move to the Aspen HYSYS. So here we are in HYSYS software. We already selected the required components, which are benzene and toluene. The second step is we have to specify the fluid package, and both are hydrocarbons. Pink Robinson would be the nice option for property package. Next step, we have to build a simulation. For that, just go to the separator and select a distillation column and drop it into the simulation canvas. Close this one, double click on it, and here just specify the stream names. So I will say it is feed, and the total number of trays are 36, and feed stage is automatically selected at 18. Stage numbering from top to bottom. Okay, so this one is condenser duty, and this one is reboiler duty, and the condenser is total condenser. This one is distillate, and this one is bottom product. Okay, so go to the next, select the one screw regular HYSYS reboiler. Condenser pressure is given, that is 9.8. Reboiler pressure is also given, that is 10 bar. Then go to the next. Temperature, we do not have temperature and it's optional, so HYSYS will estimate it for us. Next step is reflux ratio, that is given 3.88, and the liquid rate here is also given, that is 500, and then done. Okay, so this new window is open, but before that I will specify the feed stream. So the feed is saturated liquid. So saturated liquid mean vapor fraction is 0, and pressure is given, that is 10 bar gauge, and molar flow rate is also given, that was 1000 kmol per hour. Now go to the composition. Benzene and toluene both are 50-50% in mole, so 0.5 0.5 as a mole fraction for these components. Okay, now double click on the column. Okay, so this window will appear. Go to the monitor, and here you can see the degree of freedom is 0, so we are ready to run the simulation. Okay, so it successfully converged, and we have here temperature profile versus the tray number. Okay, so for checking the performance, go to the column profiles. You will have here reflux ratio and boil up ratio, and temperature, pressure, and net liquid and net vapor flow on each plate. Okay, so but here I am interested to see the separation. So in distillate 99% benzene, and in bottom 99% toluene, so it matches our desired specification. So energy balance and material balance is okay for this column. So let's move to the hydraulic profiles of the column, or column internal designs. For that, just click on internals. Okay, here you can see the column has a gap 1 to 36, means we did not specify anything inside the column. So here you can add in two ways. If you want to have the same column from top to bottom with the same diameter, you will add only one single section. But in if we see in refinery, the actual distillation columns, they have sections. Okay, the section above the feed tray is called rectifying section, and below feed is called stripping section, and the diameter of the stripping section is a little bit bigger compared to the rectifying section. In this way you have you have a more optimum design. Okay, so here we can see that in yellow bar that internals calculations completed with warnings. So here the tray types is sieve for both section, for rectifying section and stripping section. To understand where is the problem, internal calculation, so we will click on hydraulic plots profiles. Then this new window will appear. Okay, so we can see that our whole column has a warning. So the warning is it says that the side downcomer exit velocity is greater than the limiting velocity. Okay, that is 0.56 for our case. So how we can cope up with this problem? So you can see this graph that is in between the vapor mass flow rate and liquid mass flow rate. So we are operating here. Okay, so and we want to move this point a little bit here to avoid this kind of warning, because if I talk about this graph, if the operating point is above this line, then the column is in flooding condition. Okay, and it is below this line, then it is in whipping condition. And if it is in between this area, so it is the warning area. So it's almost going to I mean, here the it is 80% of the design of the wear height, but we can change either the this parameter, or we can also increase the tray distance, so to avoid the entrainment. Okay, so how we can do that, you will see here. So the tray spacing, you can see for section is 0.6. so if I increase from 0.6 to 0.8 and then see, so the warnings, okay, just a moment. So you can see the top almost until stage number 6 we remove this condition. Okay, we remove this warning. So similarly I just increase a little bit more, 0. maybe 82, and similarly for the downside 0.83. okay, so let's see how many plates are there with warning. So the down side of the column is completely fine, but the tray number 14 to 17 still have this problem. Okay, so this is one way to avoid these flooding conditions. So instead of 0.82, maybe 0.83, and then see. .84. okay, so now you can see that the on left hand side that the whole picture is blue. It means now it is away from the boundaries of whipping, flooding, entrainment, and dumping. Okay, so this is the optimum design for this distillation column. So these are the vapor flow rate profile and liquid flow rate profiles inside the columns, and the geometry is perfect. So this is the way how you can specify, design distillation column internals. Okay, so this is one way to avoid the warning, just enhance the tray spacing. But depending on the warning, you have to take action. For example, sometimes you have to change the column. For example, the plate type. Here the default one is the sieve plate, but you can have bubble cap and many others. Okay, and also you can adjust the plate geometry, even the hole diameter, wear height, side wear length, and everything. I mean, according to your available data sheet, you can just put the values and HYSYS will perform calculation like a calculator. Okay, so I hope you understand the importance of internal design in distillation column, because it will, for example, if you uh, increase the diameter, okay, and then obviously it will reduce the length, but if you decrease the diameter it will increase the length. So all these factors uh, put an important role in cost of your project. Okay, so that's all for today's lecture. Until next video, stay tuned, take care, bye bye.